It's great to be here. I think it is the most challenging talk to give as the first talk in the afternoon session, because we all in a post-food coma a little bit. So I hope we can cheer you guys up. So the talk I'm going to give actually is a joint work by multiple institutions over the past 4 years. I was fortunate to have a great team to work with me. So I'm going to start with some of technology and how we come to this application. So we are actually roboticists. So we come to the natural observation domain. So we are actually a group of roboticists called a teleoperation expert, which means we investigate how to bring the human to work with machine using communication channel. Okay, this is one of the examples you can see. And the earliest telerobot, actually, modern telerobot is invented by Nikola Tesla over 100 years ago. Actually, this is probably beyond most of us knowledge. It's actually just the invention of the radio control, radio at the moment, and he came up with this brilliant idea at the time. So and then the teleoperation domain develops, and the primary driving force behind it is the application like in the nuclear material handling and the space applications, until something else happened in 90s. This is actually first the internet-based camera system being put on the internet by a group of 30 students in Cambridge. So you can use the webcam to, actually not webcam, but the camera on the internet to observe the coffee pot before you go downstairs to grab a drink. So it gives you an advantage, right? And in '94, Professor Ken Goldberg put up a first robot on the internet to allow people to attend a garden over the internet. That's actually the first robot on the internet. So we kind of invest quite a bit on this domain, trying to study a particular type of problem we call collaborative control. Basically, you're trying to allow a group of people to control a single or shared limited number of resources. So in this case, we're looking at the robot as the agent. But if you replace robot with the robotic camera, this actually is it's a system that allows multiple people on the internet to sharing a physical device that allow you to interact with a remote environment. How do you ensure that the sharing can happen? This actually we come up with called collaborative frame selection problem, which means we have these two windows. The lower window is a panorama indicating the reachable view of the camera. The up window is the live view. So basically, people can specify where he wants the direct camera by drawing a rectangle on the lower panorama. The camera responds to it and move to that location, showing the video. And when you have more than one request, the problem becomes mathematically, we call it the frame selection problem. You have to solve the problem in a very fast fashion because those requests can change, and actually requests not just come from human, it could come from online sensors as well. For example, your acoustic device find a bird that want a direct camera to investigate it. So we call this called the frame selection problem. Over the years, we spent quite an effort trying to solve a bunch of frame selection problems and different problem contexts, which is summarized in my recently published book. So what are we really thinking is this gives us an opportunity to apply this technology to a new domain, which is biological observation. What do we learn from the domain experts is the biological observation has one demanding aspect. You need to spend a lot of time to observe the nature. So basically, even for the seem to be familiar objects like lines, we only know about 3% of their life. With such limited knowledge, you cannot declare that you know all things about lines. But observation is very labor intensive. How are we going to be able to do this by providing a new type of system? So we actually propose this cone idea. Basically, it's a combination of the multiple people on the internet, which people spend a lot of time on the internet, may or may not be productive, to harvest this time, and in combination with the automation, which is sensors and pre-programmed logicers, together to collect data for natural science. Okay, so we begin with automated end, which means first of all, you have to make a sensor smart enough to work with human. But in this particular project, we actually get involved into a searching of Arabia woodpeckers. So how many of you heard about this bird? Okay, great. So this is a very high-profile bird, and this is called the holy grail of bird watching because this bird actually last seen in 1940s, and this is the picture they taken, and the image, the image you show is actually the artistic rendering. It's not the real bird. And at the last time it was documented, it was by the Cornell University. This researcher bringing the cutting technology from Hollywood, loaded on a wagon, and drive to the Louisiana to listen to the bird, at the time, the most cutting-edge video audio device to record the bird. And they were believing this bird was last in America. So after they observing the bird, take the recording, they kill the bird. It's upset, but that's the. I'm thinking this bird probably somewhere in some museum, and you can still find its model. But since then, there were a lot of sporadic sightings. Nobody actually has concrete evidence as like clear picture or a clear video recording of this bird. So and on the other hand, a lot of people develop camera systems trying to deploy in the field to capture the birds. And Greg will talk more about the critical camera system. Those technologies are developing. But when we apply this part of technology into the field, we immediately face a problem. No camera can tell is that a bird fly by, first of all, or it is a Arabian or not, Arabian woodpecker or not. Those type of questions cannot be answered by current technology. So, and besides, this bird usually are very shy. They want to live far away from the human population. So the environment they live in is very remote, very difficult. This is a place they were having a sighting, and actually non-confirmed sighting in 2004 in the central Arkansas. And this is a place called, it's somewhere in between Little Rock and Memphis, in the middle of nowhere. We're going to see more of a picture of this location. I'm trying to develop a system that can work in this environment and also helping us collect data. So we designed the physical component, trying to see if this is what we want to do. And we want to make sure this thing can work 24/7 without for extended period of time, because visiting this place is so difficult. So we put a lot of design on the reliability of the system. But what really most important thing is, can you detect the bird? Well, first of all, we begin with most of the people know about this motion detection. If something triggered by a motion, it might be caused by a bird. So we implement a motion detection by filtering out the background noise, especially periodical movement. At the time, we found out when we put on a test, our system was able to capture the sunstorm strike on the back of the building. So we were encouraged by how fast our system can respond to a motion, and also not taking into the background noise. Actually, this is a rotation. It's a weather radar. It's rotating all the time. On the background, we were able to filter this thing out. So periodical noise like tree branch vibrations and the sound movements, we can deal with that. But we still have, we were able to capture a lot of birds in the urban area, which this is actually a pigeon, rock pigeon diving in front of the camera. We are pretty happy with that because, well, this bird is smaller than Arabian woodpecker. It's supposed to be hard to detect. So we'll say, okay, let's do more of the field test. But one type of thing we have to do is the system automatically segment the bird sequence, so it can study the bird even in close detail. But it's not our problem has been solved yet. When we were doing the field test, we found like the moving clouds is very bad for us because when we're trying to capture bird on the fly, sky is always the background. The moving clouds can create all kinds of noise with all kinds of signature. So it's just not able to filter out if you don't do a little bit smarter image processing. So we have to study bird flying dynamics, looking at what in dimension didn't change during flying. So we will be able to confidently say actually during the flying, the body axis is rather stable because it has to extend the body axis to parallel to the flying direction to reduce the wind resistance. And also, if you look at a sequence of the bird flying image, you're going to see that this body axis has pretty close to the trajectory itself. The bird flying trajectory, if you look at a long distance, the bird flying trajectory is irregular. But if you look at a fraction of a second, you can treat it as a linear trajectory. So that's what our system was doing, just looking at a fraction of a second to see if this bird is the type we're looking for. So we're also doing all this extraction of body axis. So by doing all this processing and putting together a filter, we were able to extracting more reliable bird information out of the noisy data set. So we can reduce a tremendous amount of data that taken by the camera. We have 2 live video cameras, each of have 3 megapixel, scanning and at 32 frames per second. There's a lot of data. It is not able to transmit or store due to the hardware and communication limitations, and you have to filter it down. So when we were installing this is the installation side of the camera. This is actually very difficult to assess. We have to drive 500 miles and then do a 8-mile off-road driving on a SUV, 4x4 SUV, to get close to the edge of the forest. Then we have going to the swamp on an ATV, towing a boat, and then we boating for another 800 foot to reach the place. So it is a disaster. So this gives you an idea how to get there. So you have to make sure your system is absolutely reliable, because it's just impossible to send the student back to fix it. Okay, so this is how the system looked like after it was installed in one of the power pole. Actually, we were very lucky to have the power option available. Locals even sponsor us a power transform for this project, which is incredible. So you see, this is actually kind of support you would expect from local. They actually really believe they have the bird. So we put the bird in one of the menu in the restaurant. So we believe it. And it's up to us to find it. So after the system's running, you can see we capture a lot of data. This is a red-tailed hawk captured by our system, and that is the blow-up view of the flying sequence. And this is red-tailed hawk is bigger. This bird captures the northern flicker. Northern flicker is a smaller woodpecker compared to ivory-billed woodpecker, and red-tailed hawk is bigger. So we were thinking, within this envelope, if the ivory-billed woodpecker fly by, we should be able to catch it. The system should have the capability. And the system is also able to capture a group of birds. This is the results based on motion detection only, not the bird identification. When this is the image that got us actually excited. It looks blurry, but in one of the snapshots, we found the white color feather underneath the wing. We found it because that's the characteristic that distinguishes ivory-billed woodpecker from pileate. But after looking at the entire sequence, we are able to tell this is because of special lighting condition. This also tells you how easy people can misclassify this bird, because these 2 types of bird, pileated woodpecker and the ivory-billed woodpecker, are so close to each other in color patterns. So it's just no wonder people may make wrong decisions. So after 1 year of running without any problem other than a power outage, which is not a fixable problem by computer science, we didn't find a bird. Okay, we got a lot of media calling us asking whether you found a bird or not. We have to say no, we didn't find it. But our system have proven to working reliably for this extended period of time, collecting enough data on our website. I think it's enough for us to study for 5 years to further improve our bird detection algorithm. So what I really want to go into is the newer project we have is the tracking the bird range change in the South Texas, which is the one I mentioned by Dale earlier on. So this is one of my friend John Rappel from Smithsonian. He actually spent his whole life studying the birds in Texas. He wrote a lot of books, and his career started in Texas. And for a few years before he returned to Texas, he immediately found a probably dozen type of species not supposed to live in Texas actually appear there. Those are local birds. They are non-migratory. They're not supposed to show up there. So he's excited because he thinks he found some bird range change evidence, but he needs our help to see to what extent those birds establish the residency. They're supposed to live in Mexico. Now they immigrate to Texas illegally. So we want to track that element. So our project, as you've seen before, we were trying to engage in the citizens from on the internet to observe nature. Use their intelligence as a data collection mechanism. Because you know that no matter how smart we are, the detection, the artificial intelligence, the pattern recognition are very primitive in telling the species of the birds, in distinguish those different flying patterns, stuff like that. But humans are extremely good at it. If you're putting all these people together, they can really make a big difference in observation. So we designed is called cone world project. As you can see, it's still a two-window structure. The up panorama you saw here is a place we set up the camera, and lower window here is the live view. So let me show you the camera right now. Hopefully it still works. So log out, log in again, I guess. So the camera is online 24/7. Anybody can go to the website, register, get an account on it. If you log in, you can view the system as I view now. I can turn on the camera. The video will be streamed to your web browser, and you can draw where you want to see it, on this side. So it's live. But what's really interesting is not just as a webcam, it allows multiple people to log in at the same times, allow people to chat with each other, to form a community. This is not the best time for bird watching because usually those people get up early in the morning. Bird activity happens early in the morning. That's why we call early bird. Okay, I'm a late bird, so it doesn't happen right now. So what's happening is, I can show you some of the data gathered here. Early today, the people were taking the image of the activities going on in these bird feeders. This actually, since we are observing local birds, they are non-migratory. So using feeders will not change their behavior because most of the birds we are observing are territorial. So no matter you place a feeder there or not, those are the birds that will live in that region. Okay, so this will not create a bias in the data. So basically what they can do is to click this button to take a picture of the system. So this, okay, so they say snapshot taken means this picture is entering the system, supposedly entering here, and this is a picture I just took. What the people can do is they can create a zoning on the picture being taken and also comment on each of the picture, give them ratings. Let's just pick up, let me delete this one because it really doesn't contain any birds, okay? So if you look at an existing picture, you will see it contains zoning, so people can attain zoning. They also can comment on that and also provide classification if they do have the knowledge. So it creates a database for us to keep track of the interaction centered around each of the image. So we can actually do a little bit of processing of the discussion, trying to extract information of the bird from there, instead of doing very sophisticated bird classification based on image itself. So this is actually, on the other hand, whenever you take a picture or give a comments, we have a scoring system. Keep track of your participation and the quality of your picture and your comments. So you got a rewarding point. Okay, so that means if you are more active and you have more expertise, you're gonna get more points and you participate more, and that points essentially also weight the control of the camera. If you have more points, your weight of you can control demand the camera more than other people. So they give you some sort of authority. So people have some sort of the reward associated with that. That actually help us to gather a lot of data because it's a gaming aspect being introduced. The gaming aspect being introduced there. So I already talked about this. So this is the number of the image taken in 1 year period. You will notice that we have April 2008 and April 2009. We have 2 downtime because we were maintaining the site at the time. So that I don't have a regular load. And so we have regular about 2,000 to 4,000 pictures per month be taken and be annotated by the user. So later on, the biologist can really use those data. This is one type of data the system can generate. This is a species based analysis of the images and comments, we can generate the species chart. What's the percentage each of the species showing in front of the camera? And be automatically generated by the system. It's updating every moment. And so the biologist can really look into the data, see how many things we can find in this region. Actually, our system can found 83 different species in the past 1.5 years. And also, for particular type species like green jay, this is one of the our primary target that is showing the range change. We can pull out the activities related to this bird, say how many times it appears in front of the camera and being caught by us. So we can draw such dynamics to let people to see whether this bird established regular residency. And actually, furthermore, those birds, most of them are color banded. We can even identify them and also the social relationship in front of camera if we really want to do so. So over the 1 year period, for the 15 type of birds that John suspected has the range change, we actually found 8 of them being confirmed by our system. So it's quite encouraging for us. So we are still collecting data. So if you are interested, please go to our system, become a data contributor. And this is the website for the Cone project. That's all.